able to get him to come down here and talk about the search for life and intelligence in the universe. And so without any further ado, actually I'm going to mic you up so that people can hear you if we can do that. So put that in a place that's convenient.
How's that?
Do you hold that right?
Thank you.
Now try.
How's that?
Yes.
Good.
Awesome.
All right.
Good.
So we'll
Maybe a little too loud. No? It's good?
Good.
All right, great. Great.
all right, well.
Right. Well, thank you for having me here, Drew. I appreciate the invitation, and I'm very, very excited to be here. This is fantastic. I actually have never been here before, and it's a great place. I'm thrilled to be here. So I'm going to ask some big questions in this talk, and right off the bat, I can tell you I'm not going to give you the final answers. What's exciting, though, what I find tremendously exciting about this area is that right now we are living through this amazing period of discovery. It is actually literally a golden age in astronomy right now, and 50 years from now people will be writing about this period of time where our understanding of the universe changed day to day, week to week. We learned new things. It is absolutely amazing, and so if you take nothing else away from my talk, take this one thing away, that right now we're living through this golden age of astronomy. We're finding planets around stars which are not our sun, but other stars. And we're very, very, very close. We're so close to finding a twin of the Earth, like a planet around a sunlight star in the habitable zone with water on the surface. We're so close to finding it. In fact, well, you'll see as we go through the talk. So it's a very exciting time, and I'm hoping that in the course of this talk, I'll be able to convey some of that excitement to you guys. So the topic of my talk is, are we alone? And like I said, I'm going to ask you some big questions. And the big questions are questions like this. How do we get from a very simple Big Bang, which is on the scale of things, it's a very simple thing, right? We start from a single point, nothing else in the universe. How do we get from there to Bach and Beethoven? How do we get to that level of complexity? How do stars form? Where do planets come from? Here you can see the absolutely gorgeous images of the Eagle Nebula. This was released this last week. New images from the Hubble Space Telescope commemorating the original Pillars of Creation image. This is basically, you can see these pillars of gas and dust and glowing with the light of newborn stars up here. So these newborn stars up in the tips are boiling away the clouds of gas and dust. And this is the same image in the infrared. It looks like a spooky claw of some kind, right? It's very cool. So we're beginning to learn how stars form. We have started to learn how planets form. So here, for example, is a star called Beta Pictoris. And as you look at it in the infrared, as you look at it at shorter wavelengths, which are hotter, you can see the star in a little bit of a disk. And as you look at it at cooler wavelengths, you see a bigger disk. So you can see a large cooling disk around this new star, around this young star. And that's where eventually we'll have planets forming in this disk going around this star. So we've started to understand how stars form, how planets form. But the questions that we don't yet understand is how we get from interstellar chemistry to life. And then after life, is intelligence inevitable? Does intelligence always arise if there's life? On this progression of questions, we go from science to belief. And the whole quest of our science is to slowly push the threshold forward so that we are not relying on belief or what we think about it, but rather what we know and what we've discovered. And again, today I'll show you some of the ways in which we've made progress on pushing this frontier forward. And so, is intelligence inevitable or is it vanishingly rare is a big question. I will not have an answer for you today, but we're close. Is there other intelligent technological life in our galaxy? And if so, can we detect them? Can we communicate with them? So, before we go further, as Drew mentioned, my name is Shami. I'm a research associate at Cornell. I got a PhD at Cornell working mostly on radio astronomy and specifically on neutron stars. After that, I've lived in New Mexico. I've actually worked at the observatory at the National Radio Astronomy Observatory there. I've worked at the Center for Astrophysics in Boston. And then I've lived in Sydney for several years. I've worked at the University of Sydney, and I've worked at the Australia Telescope National Facility. And now I work at Cornell mostly on gravitational waves and neutron stars, but also on some of these topics. And so hopefully I can tell you more about them. All right? One other thing I want to emphasize, please feel free to interrupt me with questions. I'm very happy to take questions anywhere in the talk, okay? And no question is too small. If you have a question, please just ask. All right? Okay, so, are we alone? There's something called the weak anthropic argument. There's a principle called the anthropic principle, which is, and this sounds really stupid when I write it, but it's actually somewhat profound. It's something that you can look at and chew over, and you can go back and forth saying, this is really dumb, or this is really profound. No, wait, it's really dumb. No, wait, it's kind of profound. The principle is this. If the universe was not capable of supporting life, we would not be here to ask the question, is the universe capable of supporting life? Right? So just by our existence, we know that the universe is capable of supporting life. And then there's a second part of this, and that's, in fact, the namesake of this observatory, Nicolaus Copernicus, and the Copernican principle, which says that on a cosmic scale, we are not likely to be exceptional. The universe is so big and so vast that it's very likely that we are not unique in the universe. If you put these two things together, then you should say, well, the universe is suitable for life, as we know because we exist. The Copernican principle says we're not likely to be exceptional, we're likely to be about average. We don't know anything else about it, so we're about average. If so, well, there should be plenty of life, right? Maybe, maybe not. These ideas were not without controversy. So here's a statue now of Giordano Bruno. He was an Italian friar, and he proposed that the sun was a star like all the others, and that the universe was infinite, and there was an infinity of inhabited worlds, and some of his ideas did not go over so well. So he was convicted of heresy in 1600 and actually burned at the stake. So that did not go well. These days we don't push things to quite that level, right? Which is lucky for some of us. All right. So the point is that there's billions and billions of galaxies, as Carl Sagan was fond of saying, there's billions and billions, right? I mean, each of the dots in this image, every dot except this one, which has diffraction spikes, every other dot in this part of this image is a galaxy, right? This is from the Hubble Deep Field, Hubble Ultra Deep Field. This is a tiny section of it clipped out. Every dot is a galaxy, and every galaxy in there is full of stars, right? Full of stars. And the sun would be one of these stars. So what do you think? Is it likely that of like the billions of stars like this, just one of them has planets which has life which is intelligent?
Yeah.
You think so?
Yeah.
Okay.
I'll bet on it.
Well, it depends on how you define intelligent.
Okay. Very good. Very good. Yeah, yeah. That's definitely true. Would we qualify as intelligent life?
The state of the college.
Right, okay, so that's getting into something else, right? We will not go there. Okay, so before we do that, we are, right now we have one sample, which is us. So what does it mean for life as we know it? Life as we know it, what are the prerequisites for life? First of all, we believe, and this is a very parochial belief, this is a belief based just on us, but it's a conservative belief, we think that we want liquid water, okay? Because liquid water is absolutely essential. It provides this medium in which chemistry can happen, and water has these amazing properties, right? Water has all these amazing properties which are just not very typical of other compounds. And so we think that liquid water is the most likely way for life to form. If so, then for a given star, you have to be in a very specific narrow region for liquid water to exist. So for our sun, for example, Mercury is too hot, and Venus is probably on the border of being too hot, and then the Earth is in this Goldilocks zone, it's just right, and Mars is probably just a little too cold for liquid water. right? So we live right in this Goldilocks zone, and we call that zone the habitable zone. As it turns out, again, remember, this is a very conservative, very parochial, very human-centric view of things. But in this view of things, we live right in the Goldilocks zone, just right. Now, the habitable zone then depends on the star. The brighter the star is, the further away the habitable zone is. The dimmer the star is, the closer in the habitable zone is. Right? And so all we need to do, it's very simple. We just need to find some stars and we need to find some planets in their habitable zones. Right? If only that were simple. But this is what the habitable zone would look like. Whoops. Now, what else? What other restrictions might there be? Well, we want the planet to have long-term stability. So the star needs to be long-lived. We don't want to live next to a very hot star that's going to burn out in a few million years, because we need billions of years for life to form and grow up and be intelligent and take over the planet. The planet's orbit needs to be stable. And that leads to things like, okay, well, maybe we don't want a planet around a binary star. Or maybe we do, we don't know. Right? If you're being very parochial, you'd say, well, we want a large outer planet like Jupiter so that it can keep comets away from the Earth. How many of you saw pictures of the comet smashing into Jupiter? Yeah, exactly. Now, if that were to smash into the Earth, that would not go so well for us, right? So maybe we want some big planet outside to pull all of these rocks away. On the other hand, Jupiter is not necessarily doing us a favor all the time. Sometimes it sends things inwards towards the Earth, so that's kind of problematic. One of the theories for how life arose on the Earth involves tides. It says that, well, simple life forms formed in the oceans, and then they got washed up on the beach. And then because the tide comes in and the tide goes out, these life forms were forced to undertake rapid changes in order to survive. And that's how you end up with complex life walking around on land. So you want a large moon for tides. And you stack up all these things and you go, wow, this makes it really, really unlikely, right? You need a planet in this habitable zone. You need a big planet like Jupiter. You need a large moon. This is getting complicated. And what else are we missing? We may be missing other factors. The thing that people are thinking about very hard now is, are all those things really required? Or are they just things that are nice to have? If we have them, we know that we can get there. Are there many other ways of getting to this exact point? And that is something that is subject to active research right now. I will not have an answer for you, but these are things that people are thinking hard about right now. Right? So one of the principles that was put forward by Frank Drake, and when he was an astronomer at Cornell and at Arecibo, was something called the Drake equation. The Drake equation, it looks complicated, it's really not. And the thing that you should remember about the Drake equation is that it's not telling you anything. It's a way of organizing our ignorance. Okay? So what does the Drake equation look like? It says that the number of civilizations in our galaxy with which we today might be able to communicate, that depends on, well, we start with, what's the rate at which new stars are being born in the galaxy? Some rate, and that number is maybe, let's say, 10 per year. We know new stars form in our galaxy. What fraction of those stars have planets? What fraction of those planets are like Earth? What fraction of those Earth-like planets have life on them? What fraction of those have intelligence on them? What fraction of those go on to form a technological civilization? And then at the very end is this factor, L, which is how long does this civilization live? Okay? It looks complicated, it says nothing, really. What it says is these are the factors, but what's important is this. This is really important. What's important is that it organizes the things, what we know and what we don't know. When we started purely from astronomy, we knew what our star was. We knew that the rate at which stars are being formed in our galaxy is about 10 a year or so. Okay? We know that well. What fraction have planets and what number in them are Earth-like? These are questions we have now answered. And it turns out that the fraction that have planets is close to 1. And the number that have number of Earth-like planets is large. Right? So between the two of them, we think that this more or less comes down to 1. Every star, more or less, has an Earth-like planet on average. It's pretty remarkable, and this is a discovery in the last 10 years. What fraction of those goes on to develop life? We don't know yet. There are very good arguments which say that that fraction is 1. 100% of Earth-like planets will have life on them. There are very good arguments which say that fraction is minuscule, that 1 in a million of these Earth-like planets will go on to develop life. We do not know the answer yet. And then we go into realms which are very speculative. What fraction have intelligence? What fraction go on to form civilization? We don't know. But what happens when you plug some numbers in? When you plug in some numbers, if you say that there's like, let's say, 10 stars form every year, half of them have planets, there's about 2 Earth-like planets per solar system, so that's about 10 in all. And now it comes down to, well, okay, maybe 1% form life, 1% have intelligence, and 1% go on to form civilizations. And then, how long does intelligent civilization live? If you count us as a technological, intelligent civilization from the time, let's say, I don't know, when we had strong enough radio broadcast that we could have been detectable outside. So the 1950s, right? And then you count our lifespan till, let's say, 1970, when we died, everyone died in a nuclear holocaust. Well, then we only had a lifespan of 20 years as a technological civilization. That's not very long. On the other hand, we didn't all blow up in a nuclear holocaust. We managed to survive and progress, and hopefully we're not all going to blow ourselves up. Right? If so, well, how long do we have a lifespan as a technological civilization? If that is 10,000 years, you think that human civilization will last on the Earth 10,000 years, then the Drake equation says, on average, in the galaxy, there should be about 10 or so civilizations that we could communicate with today, depending on what numbers you plug in for these factors. If you say that we are now past our growing pains and we're going to be this mature civilization and we're going to all upload ourselves to computers and we're going to live for 1 million years as a civilization, then the galaxy should have thousands of civilizations right now. Right? So this is a way of organizing our ignorance and saying, these are the factors that we need to be figuring out. And when we get to the end of the talk, we'll see that it actually, what we find for these factors tells us something about how long we can expect to live and how careful we should be, how unique life may be on Earth, right? That's something else that we will talk about at the end. Okay, so Enrico Fermi, who was a very, very smart guy, and he did many interesting things. One day, just walking to coffee, he asked his colleagues, so where are they? And this became known as the Fermi Paradox. Because remember, I just said, if you plug in reasonable numbers for this, you can end up with thousands of civilizations in the galaxy. And the Fermi Paradox says, if there's thousands of civilizations in the galaxy, some of them no doubt are more advanced than us. Why don't we see evidence for their existence? Where are the gigantic alien superstructures? Where are the spaceships? Why don't we see them? So what are our answers to the Fermi Paradox? The pessimistic answer says they don't exist. If they did, we would have seen them. Perfectly valid answer. The conspiracy theory answer is that they do walk among us, and we see all of these and the government is hushing them up. Trust me. If I knew about it, I couldn't say anything because they take away my conspiracy theory license right away. No, this is not true. You try to get astronomers to keep a secret, it's impossible. It's impossible. I mean, there is no way that this would ever work out. So, okay. Where then is this filter? What's preventing all these technological civilizations from communicating with us, if they exist? Maybe the step from going from intelligence to technology is a big step. Maybe you get to whales and dolphins and dinosaurs and you never get to technological civilizations. Right? That's a possibility. Maybe dolphins think we're really stupid because they're happy in the water and they fish and they swim and they're happy. What's the point of going on to land and getting into all this trouble? Maybe that's the problem. I don't know. I mean, they would not be broadcasting on the radio. The optimistic answer, though, is that civilization takes a while to diffuse across the galaxy. And so actually, Carl Sagan did this calculation once, and his conclusion was that given the time that the galaxy has existed, and given the time that stars have formed and metals have been available to build more complex things on, and given how long life takes to evolve, a civilization should be spreading across the galaxy just about now. And so his optimistic answer was that they'll get here, or we'll get there, any day now, right? Is when we should be seeing evidence for intelligent civilizations in the galaxy. So if you believe that, that's the optimistic answer, and that's a very exciting time, right? In the meantime, we should go out and look for them, right? Because sitting around waiting and hoping that someone will come visit the Earth is probably not the best approach to life in the universe. So, okay, so what can we do? And so this is the part of my talk. I'll talk a little bit about searching for extraterrestrial intelligence. What should we look for? One of the principles that we use is something called reciprocity, which is, again, it says, take the most pessimistic parochial view. What do we put out? Right? Whatever we put out is what we should look for because someone else might be emitting the same thing. Okay? If so, what should be detectable? What are our most detectable things? What do you think? Yeah?
Satellites?
Our satellites mostly are beaming down towards us. They're not really beaming outwards, but yeah, it's possible that you could detect transmissions from satellites. What else?
The light we emit from the planet.
The light we emit from the planet is also interesting, but it's very hard to see against the glare of our sun. Against the glare of our sun, our light is negligible. It's really hard to see. Yeah. Our radio waves are more interesting because our sun is not particularly bright in the radio. So in the radio waves, we do stick out like a beacon against our sun. Yeah, radio waves. What else?
Microwaves.
Same idea, yeah. So radio waves basically start from the microwave and go further on. Yes. So yes, microwaves. What else? What particular radio wave? I mean, you can imagine there's this shell of I Love Lucy transmissions heading outwards from the 50s. And that's probably the first signal that's going to be bright enough to detect. The intriguing thing is that eventually we switched to cable, right? We stopped beaming all these TV transmissions outwards because that's wasteful of the power. And so the Earth, for a brief duration of time, was very, very bright in TV transmissions. And now it's not as bright as it was in the 50s, 60s, 70s. Most of our transmissions have gone to cable. So there's this brief shell of emission shooting outwards from us, announcing to everyone, here we are, and then no. What else is detectable?
Well, the satellites that we put up, I mean, like this thing that we put up from Mars, and maybe something that we could transmit from that.
Yeah, space is big. Really big. It's hard. It's really hard to see because they don't have that much power. Yes?
How about the fact that we're orbiting a star? Would that be a reason?
That would not, well, sure, and that would allow us to be visible as a planet. Yes, someone could look at the sun and say, yes, the sun has planets. What they find most obviously is Jupiter and Saturn. And the inner planets would be harder to find. But yeah, we could tell that they have planets. Yeah?
How about all the SETI transmissions?
There aren't very many. There really are not very many. And they're very rare. It would require, I'll show you some of it, but it would require real luck to be able to detect it. Yeah?
What about electromagnetic,
What kind?
like electromagnetic waves?
Well, so TV transmissions would be one example of those electromagnetic waves, absolutely. Yes, TV, radio. What's actually more visible probably is things like airport radar, which is a strong signal and going all the time. That's pretty visible. There's big radio telescope, Arecibo, we use that. We light up other planets from Arecibo and do radar. Instead of on airplanes, we do radar on other planets. When that's going, that could be seen right across the galaxy. If you were in the beam of Arecibo, when it was doing a radar experiment, when it was looking at Venus, for example, or Mercury, you could see that transmission right across the galaxy.
But not today.
Hmm?
But not today.
But not today. It would take many, many millions of years for that signal to go, yes.
How
But-
about Newt Gingrich's military base on the moon when they
Right. Well, no, actually, one of the more surprising things you could detect is all of the nuclear tests that have been done in the atmosphere. Those would light up the Earth in flashes of gamma rays that would be very visible from reasonably far away, actually. But we don't do many of those anymore. And you have to be looking at just the right time to be able to do that. So, okay. Anyway, so that's some examples. There are very, very few beamed transmissions. For example, in 1974 at Arecibo, this signal was beamed once. It was a sequence of ones and zeros, and it had 1,679 digits in it. 1,679 ones and zeros were broadcast once towards a globular cluster, right? And you take those 1,679 numbers, if you got all of them, you'd say, well, that's a product of two prime numbers, 23 and 73. Let's arrange them on a grid of 23 by 73. And if you do that, you get this picture. And it's a picture of, this is the Arecibo radio telescope, here's a person, here's the DNA double helix, here's the sun and the planets. There's all kinds of things in here that would be very interesting. What are the chances that someone, well, first of all, it was broadcast once, one time. If you were listening for it at that instant, great. If not, not a chance. Yeah?
Why was it broadcast at 2.4 gigahertz?
That's a very interesting question. Primarily because that's the frequency at which the radar transmitters were available. But yeah, but that's something that's controversial. Someone would have to be looking at exactly that frequency in order to be able to detect it. Right? This was not a serious exercise. This is not a message to aliens. This is a message to us. What it was a setup for a big discussion about should this be done. If we broadcast our existence to alien civilizations, is there a guarantee that they're going to be benign? Are they going to say, hi, how are you? Or are they going to say, oh, look, there may be some interesting things there, let's go take over the planet? It provoked a discussion, really. That's not what it was about. This was not a serious communication exercise.
If it wasn't serious, why did they pick M13?
It was in the beam at that point in time, honestly, but it's a globular cluster with a whole bunch of stars. On the other hand, those stars may not be very likely to have civilizations around them. And it's very, very far away. To get there, it's 24,000 light years away. So the signal is not even a fraction of the way there yet. It's going, right? Anyway, so there was one beam transmission. So, there are a few of these beam transmissions. So where should we be looking for these transmissions? Well, the obvious answer, kind of, is if you look out at the universe, 1400 megahertz, 1.4 gigahertz, there's a very interesting line, atomic hydrogen line, and that's a clear window in which you can observe most of the galaxy, right? That's the particular frequency associated with hydrogen, which is the most common element in the universe. And so if there exist astronomers in other civilizations, they would be observing at 1420. We know that because we observe at 1420, and that's an interesting place to observe. So that would be probably where they would signal to us. On the other hand, we sent it out at 2.4 gigahertz, so so maybe 1420 is a good place to look. But what if, for example, they chose something else? For example, in science fiction, there's a famous example of hydrogen times pi, right? Because that says we know about 1420 megahertz, we know about pi, that says we're intelligent. Let's broadcast at about 5 gigahertz, 1420 multiplied by 3 point whatever, and that's an interesting signal because hydrogen times pi says we are an intelligent civilization, pay attention to us. Maybe. Who can read the mind of aliens? We have enough trouble reading the minds of each other, so who can tell, right? So what we need is some serendipity. We need some luck. We have had luck. So in 1969, 1967, this is a picture of Jocelyn Bell. She was a graduate student, and this crude-looking array of dipoles was their telescope. They were using this as a radio telescope to study interstellar scintillation at 3.7 meters, which is at 3.7 meters, so wavelengths which are this long, huge wavelengths. They were looking at the twinkling of radio sources. That's interplanetary scintillation. They were looking at the twinkling, and they were trying to figure out why some of these sources twinkle. And Jocelyn Bell, as a graduate student, she was working with this array, and she discovered pulses from the sky. This is her chart recording, 6th August 1967, and she has scribbled here Pulsar CP1919 and interference. She knows her instrument well enough that she knows this is interference. This is something interesting, right? So that's one of the messages. You really need to understand your telescope, your instrument, if you're going to do science. But from this chart recording, she found some interesting things. And they were actually labeled LGM1, the first signal, because it was a giggle joke for them, it was little green men. They thought they found possibly the first evidence for little green men. They said LGM 1, 2, 3, and you can tell from naming it LGM, they knew that it wasn't. They weren't serious about it. But still, their code names they used was little green men because they thought maybe. In 1968, Tommy Gold, who was one of the founders of the Cornell astronomy department, he predicted that if in fact this was a particular kind of astrophysical object, a rotating neutron star, then the ticks, the pulses that were coming from the sky should be slowing down. And the very next year, a radio pulsar was discovered in the Crab Nebula. Those of you who were here for George's talk, you saw the Crab Nebula he showed you. Inside it, they discovered a radio pulsar, and the next year they showed that the period was in fact getting longer, exactly as predicted. So what was found was in fact a neutron star. And this led to a Nobel Prize for Tony Hewish in 1974. A neutron star is amazing. I study neutron stars, which is why this little digression. It comes from the death of a massive star in a supernova explosion. If you look over there on the chart, you'll see a picture of Cassia, which is literally the cloud left behind by a star blowing itself apart, right? And in the center of that is a neutron star, right? It's massive, extremely massive. It's tiny. It's like a few miles across. It's the mass of our sun squeezed into a few miles. It's the densest known substance in the universe is what makes up a neutron star. And it spins very fast. It spins faster than a kitchen blender. And as it spins, this beam of light sweeps across our line of sight like a telescope, like a lighthouse beam, and we see these blips, right? So that's a neutron star. And yes?
So those signals were originally thought that could be of origin from extraterrestrial intelligence?
Yeah, so Little Green Men was the code name assigned to them, and then they basically demonstrated in a couple of years that no, they were from neutron stars. And now these are a whole area of study. They're fascinating objects. They're laboratories for astrophysics in the best way. I'm not going to talk further about them.
Dr. Chatterjee, on the array, the antenna array that Dr. Jocelyn Bell had up there.
Yes.
It looked like the antenna array at the high altitude Auroral Research Project in Alaska. The array looks very similar to that.
True. This is because they were working at low frequencies, so very long wavelengths, right? And so any long wavelength array would in fact look similar. You'd want lots of these big antennas widely spaced so that you could collect as much radiation as possible. Yeah. So there are modern day descendants of that antenna array. Yeah.
Why was Jocelyn Bell included in the Nobel Prize?
This is a very, very sore topic for pulsar astronomers. On the plus side, it was honestly, there was a little bit of sexism, there was a little bit of, oh, she was just a student, there was a little bit of, well, Tony Hewish deserved the Nobel Prize. There were a lot of factors that went in. On the plus side, when the first binary pulsar was discovered by Russell Hulse and Joe Taylor, both of them got the Nobel Prize. So the graduate student was recognized. The Nobel Committee did make it up to the graduate student. Unfortunately, not to Jocelyn Bell. Things have worked out very well for her, though. She's been knighted, and she is like, when she comes, she's like a rock star in the field. So it's worked out okay for her. Yeah. Do you have a question?
How did that message come here? That one message where it had that person?
Oh, that's actually something we sent out. So somewhere in that globular cluster, if there's a planet, someone like you might be asking, how did we get that message? They wouldn't know. We sent it out, right? I'll show you what we have received in just a little bit. Yeah.
In a way, wouldn't we just be technically chasing our own tails? Because by the time, if we did spot something of that aspect, that could possibly be gone, long gone. So
This depends, this is exactly right. And this depends on that last factor in the Drake equation. How long do civilizations live? And how many are there? If there's many, many civilizations in the galaxy, then the nearest civilizations would be close to us. They'd be just a few light years away. We could almost have a conversation with them. It would take 10 years, but still. how are you, and then you wait 10 years and you get something back from them. but still, 10 years is nothing. 10 years is almost a graduate student PhD thesis, so it's nothing. If civilizations don't live very long, and if civilizations are far apart, then in fact, yes, we would get a signal, it would come from thousands of years away, and then by the time we send something back to them, they might very well be gone. Yeah, so that's a profound problem. And like I said, what I'm going to show you is we're making progress down the terms of the Drake equation. We don't know about those terms yet. We will though. Yeah?
Doesn't the strength of the signal go down as it is transmitted?
That's right.
I mean, how far can our signals actually truly be still detected?
This is absolutely right. The signals do lose strength as you go further away. They fall off rapidly. Our radio telescopes are extraordinarily sensitive though. And so the metric we talk about is if you had an Arecibo-sized telescope at the other end of the galaxy, and we transmitted from Arecibo, they could detect it. Right? So it's possible to use radio waves right across the galaxy. The bigger problem is the time. Radio waves only travel at the speed of light. Nothing exceeds the speed of light. It's like it's better than any speed limit. It's the law. Nothing goes faster than light. And so because of that, the time to cross these distances is so large that that's a much more limiting factor, I think. Yeah. Okay. So what have we done so far for searches? Well, Project Ozma was something that Frank Drake started, and he looked at 2 nearby stars. There were these surveys which went by the name of Serendip, and then there was a big NASA survey which was cancelled in 1993 because some senator got up on the floor of the Senate and said, we're wasting taxpayer money on looking for little green men, and so that was the end of that. On the other hand, that was revived as Project Phoenix entirely with private money, and so right now all of our SETI searches are entirely private. There's no taxpayer funding for SETI right now.
What is nearby?
Well, a few light years.
A few light
Yes,
years.
yes, not too far.
Who's funding it?
These are all private. Project Phoenix is there's this thing called the SETI Institute, and they're a private organization. They raise money and they piggyback on our surveys at telescopes, and they were building their own telescope called the Allen Telescope Array with funding from Paul Allen. So yeah. All of this is now private, and there's no, yeah, it is interesting. There's no confirmed detections, but there are a few tantalizing candidates. This one goes famously by the name of the wow signal. And the reason it goes by the name of the wow signal is that someone was using a chart recorder, and the chart recorder was set up. These are frequencies, frequency channels. This is time at their radio telescope. And most of the time, you either get nothing or you get a 1, which says there was a little bit of noise, right? Nothing, nothing, little bits of noise, and then suddenly it goes 5, J, U, Q, E, 6. So off the charts bright and then back down again, and that's it. And he circles this with a red pen and writes, wow. And it's never seen again. Not ever. Okay?
Civilization is done there.
So, it could be, the optimist would say, just like we sent one signal towards this globular cluster one time, someone decided to send out one transmission, and we happened to be along the line of sight, and that's what we got. Someone else would say, nah, this is just interference. Right? It's someone turned on the microwave next door. It's probably not the microwave next door. But who knows what it is, right? This is the problem. With one signal, there's no way of making any further progress on it. It's probably not the microwave. It's probably not ET saying hi, but it's never repeated. Many people have spent a lot of time going back towards where that telescope was pointing and looking and never seen it again. So this is a famous little example.
And what do the letters represent?
Oh, they're just amplitudes. They're just numbers. So it goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, all the way to. So when it goes to J and then U is like way out there on the scales. It's a chart recording. So if they had higher time resolution, maybe they'd have seen lots and lots of digits there. Maybe it was broadcasting the digits of pi to us. We'll never know, because that's all that is. right? So, tantalizing candidates. What about closer to home? What about life in the solar system, right? Before we go chasing off around other stars, what about life nearby? Our nearest neighbors have always fascinated us, most prominently Mars. Schiaparelli, Percival Lowell, they looked at Mars and they saw this network of canals, and they saw the canals come during one season and go away during the other season, and they came up with this idea of this doomed civilization on Mars, which was digging canals to bring water from the poles down to their fields and so on. And then we got better telescopes, and it turns out, nope, none of that. On the other hand, right now, there's this famous picture that went around. Mars is the only planet that's inhabited entirely by robots. Right? This to me, this is an amazing picture. This is an amazing picture because this is the opportunity robot on the surface of Mars that we're taking a picture of with a spacecraft that we have going around Mars. So it's a robot on another planet taking a picture of another robot on that planet. It is amazing. I mean, you can see the rover's tracks, you can see the rover itself, you can see the shadow of the camera mast. We have rovers walking around on another planet. How cool is that? I mean, that just blows my mind every time. It's amazing. So this is the surface of Mars. We have rovers there looking for life. Looking for evidence of geology and biology and possibly liquid water because of the biases we sense. Now, can we do this in a simpler way? Yeah, question.
Do they know if we're ever going to be able to walk on Mars?
Are we ever going to be able to walk on Mars? If we can get there, we certainly will be able to walk on it. Can we get there? This is a hard question. Okay. The goal is yes. The aspiration is yes. But yeah, it's a hard question. However, can we get samples of the solar system without going all the way to other planets? Turns out the answer is yes, because we get rocks from space. We get meteorites which land on Earth, right? And it turns out that you can pick them up and you have samples from other planets right there. Now, what's the best way to find a meteorite? If you were to design a meteorite catching experiment, how would you do it?
Magnet.
They're not all magnetic. So the problem is when meteorites land on the Earth is full of other rocks. One rock landing, yes?
A big flat area where there are no other rocks. So
that's exactly right. That's literally exactly right. And what you'd want to do is you'd want a big white sheet, right? And luckily we have a big white sheet in Antarctica. And so these are people actually looking for meteorites in Antarctica. They go down to Antarctica and they get on these little scooters and they go across the surface, and every once in a while, there it is. I am not kidding. This is Ray, this is someone I know, and this is him finding a meteorite from somewhere else in Antarctica. This is how you do it. Because look, there's no other rocks here. This came from up there. It has to. Right? It's that simple. You go, you pick it up. Yeah. Okay, so you pick up these rocks, and then you take it to the lab, and you cut it open, and you look at, there's little bubbles trapped inside it from which you can get gas compositions, and the gas composition tells you which planet it came from. So this is a rock that came from Mars. It goes by the name of ALH 84001, which means it was picked up in the Allen Hills region of Antarctica in 1984, and it was the first one to be picked up that year. Okay, you cut it open, and in 1996, scientists announced that they'd looked at it and they found the title of the paper was Possible Relic Biogenic Activity, which means relic as in fossilized activity that came from life. The big qualifier in front was possible, right? And this is their electron microscope photographs of the inside of that meteorite that was picked up in Antarctica. And they showed these little bumpy things, and they showed these structures, and they said, these are possibly nanofossils. These are possible nanofossils, and if so, this would be evidence that life arose not once but twice once on Earth and once on Mars. If you believe that, right? Now, Carl Sagan had a famous saying which says that extraordinary claims require extraordinary evidence, right? This is great evidence, but it's not extraordinary evidence, because since then people have come up with ideas which say, well, you could mimic these signatures with chemistry, not necessarily biochemistry. You could do it with chemistry. So it's very, very interesting. It's possible that this is in fact life, but it fails the extraordinary evidence requirement. Okay? So this is tantalizing, maybe, but probably not. Okay, so most astronomers today would tell you, nah, we don't really believe that that's evidence, good enough evidence for life. If we were to show in some other way that Mars did have life, that would also be supporting evidence, but it's not enough on its own.
How did those people get to Mars to collect the samples of those labs?
They didn't. This is the fun thing about it. They collected the evidence like this in Antarctica. Because rocks from Mars were blown off of the surface of Mars by volcanoes or by other things crashing into Mars, and they travel through space. And then they come down on Earth as meteorites. And if you step outside, you can see meteorites that they have in the collection here that have been picked up. And they come from other planets, sometimes from Mars, sometimes from Venus, rarely, mostly from asteroids. But some do come from Mars.
So we know they're from Mars because
Because you cut it open and you do this gas isotope chemistry. You do the gas chemistry and it tells you where it came from.
and you know that Mars's atmosphere composition.
Yes, that you can measure from Earth just by looking.
Okay.
Yeah, with a spectrum you can do that. Yes?
I was just seeing the news about the organisms that we found
Yes.
in Antarctica, under the water, where
Yeah.
we thought no life could exist.
Yep.
And if we're going just by a habitable zone, maybe there's life that can like
This is a very good point. And so in fact that's exactly my very next point, is that you could have life finding footholds in environments that we don't think of as possible places for life. For example, Europa, or maybe Titan. If you look at the surface of Europa, you see these rafts of ice flows that have broken up, because Europa very possibly has a liquid water ocean underneath its surface of ice. So it's well outside the habitable zone. On the other hand, because it's close to Jupiter, the tides keep the ocean liquid underneath it, under the ice. So there's liquid water. It's just not in a place that we would think of, but it's there. Could it be a source for life? This is right now the hottest target for planetary astronomers. They really want to send a probe to Europa to see what's under the surface of the water. Yeah. Is there a question in the back? No.
Is the moon really made out of cheese?
We'll have to step up and see. Right? Yeah. Okay, so could we then, if we were astronomers and we were looking at the Earth, could we tell that the Earth had life? And the answer to that is almost certainly yes. If you could look at the Earth, you could tell that it probably did have life. How? Well, this is what the spectrum of the Earth looks like. You take the light from the Earth and you look at what's in there, and you can see evidence for the existence of oxygen. You see water and you see ozone. And if you compare that to the other planets, here's what the spectrum of Venus looks like. There's a big dip for carbon dioxide and pretty much nothing else. Here's what the spectrum for Mars looks like. Big dip for carbon dioxide, pretty much nothing else. Here's what it looks like for Earth. Big dip for carbon dioxide, but also dips for water and ozone. And the existence of water and the existence of ozone tells you not just that life could exist, but that life does exist. Because if there wasn't something putting oxygen back into the atmosphere, the oxygen would react with iron and form rust. And that's what makes Mars a red planet. The surface is full of rust. Because the oxygen has reacted with iron, there's no oxygen left in the atmosphere. The reason we have a dip for oxygen is that something is pumping oxygen back into our atmosphere, which is what? Plants. And that's evidence for life. So it's not just that we could tell life could exist. We would know that life does exist if we could see that. Right? So the race right now is to find the spectrum, not just to find planets, but to find planets and take their spectrum. And so for the last part of my talk, I'll just talk a little bit about planets beyond the solar system. And I'm kind of running a little bit late, but bear with me on this, because this is where I think is the most exciting stuff. Till 1990, we knew of 9 planets around one star. Right? That was 1990. In 1992, using the Arecibo radio telescope, Wolshan and Frail, they found 2 planets around a neutron star, around a pulsar. So they found around a pulsar some planets. And these planets were tiny. They were only like 3 times the mass of the Earth. So they were small planets that were discovered around a pulsar. Now, around a pulsar, there is no way that you can have any life. So it wasn't very interesting in that sense, right? But it showed that it was possible to find planets beyond the solar system. Since then, with a combination of many different techniques, we've found many new exoplanets, extrasolar planets. How can you find them? You can just go look at a star. That's really hard because you're trying to find a planet against the glow of the star. And here's an example. Right in the center is Fomalhaut. It's being blocked off with a coronagraph. And the dot in the middle shows you where the star would be. Right? The star's light is blocked off. If you block off the light of the star, you see this disk forming around it. And right in that disk, you can see this speck. And that speck seems to move over time. It's a forming planet. It's a baby planet. It's not a real planet yet. But you can see a planet forming around the Fomalhaut system. Right? That's direct imaging right there. It's really hard because you have to block out the light of the star, and you can see that even after blocking out the light, it spills over. It's very hard to do. You can do it. I won't dig into stellar radial velocity, but there are techniques by which you can do it. You can look at the star wobbling back and forth, and you can tell that there are planets tugging on it. Or you can do it with transits, and transits are the simplest way, and I'll show you transits in a second. And then there's microlensing, which is one-off, and we won't talk about it. Well, finding exoplanets, we knew of 9 planets before 1990, and since then the number of planets we've been finding has been increasing over time. Rapidly increasing over time. And today, we know of over 1,500 planets outside the Earth, outside the solar system. 1,500 planets we know of today. Right? These are not candidate planets. We know around those stars there are planets. And this has been a revolution in the last few years. You can see in 2000 and onwards, the number of discoveries per year has just been ramping up. We live through a golden age in astronomy right now. Right? One of the transformative things in here has been the Kepler mission. And the Kepler mission is a space telescope which just stared at this one patch of sky in the Cygnus constellation. It stared at that one question. Yes, sorry.
You're fine. I just had a question about the planets. Why are we so focused on just planets? Because as you said before, life is it's possible that they could exist on moons and
this is absolutely
other objects.
Right. Yes.
So why so focused on planets?
It's a very good question, and the answer to that really is we want to be as conservative as possible. So what we're looking for in the most conservative sense is life just as we know it. And life just as we know it is life on a planet around a moderate, healthy star. Right? So that's what we're looking for. If we find something more exotic, great. We're also looking for that. But this is sort of where we're spending the most effort because that's what we think is most plausible. Right? That's not to say other things are not at all likely, but this is what we believe is the most possible. Okay? So we know of lots of these planets now, and thanks to Kepler. What Kepler does is very, very simple. It looks at a star, and it very accurately tracks the amount of light coming from the star. And if a planet crosses in front of the star, it blocks the light of the star by a teeny tiny amount. Teeny amount, and it causes a dip. And we look at that dip and we say, that's interesting, and we keep staring at that star. And a little while later, the planet comes back around and it causes another dip. And we say, that's very interesting. And now we have a prediction for the 3rd time we should see a dip. And we wait, and if at the 3rd time, if there is a 3rd dip right at the predicted time, we say we found a planet that's passing in front of the star. This is very unlikely because you only find a planet when it's right edge on. And yet it turns out Kepler has been amazingly successful at finding planets. Here's Kepler 4, 5, 6, 7, 8b. Okay, these are the 4th through 8th planets that Kepler found. And you can see as the planet passes in front of the star, this is real data. Steady, dip. Steady, dip. This is the shadow that the planet casts on top of its star as it passes in front. And these dips, they look big, they're tiny, but we can detect them very, very reliably. And that's one of the amazing things that Kepler did. Now look at the orbital period. 3 days, 3.5 days, 3 days, 5 days, 3.5 days. Why do you think these orbital periods are so short? Yeah.
Either the planet small or the stars small?
Well, that's certainly true. The planets are pretty small, but this is because the planets are close to the star. But why do you think we're finding all these planets with such short orbital periods?
Because the speed of the planet is going by at a great speed for some reason.
Well, yeah.
Because it doesn't have a moon?
No, not a moon. A moon would be too small to see. No, it has to. It just has to do with it has to do with nothing about planets and everything about astronomers. It's that we can see these transits happen. Like I said, it takes 3 transits to find it. How long would it take for Kepler to confirm a planet like Earth? 3 years, right? How long would it take for it to confirm a 3.2-day planet? In 10 days, it's seen it go by 3 times. They published the paper 10 days later, right? Not quite that simple. But still, more or less, that's what it is that we are very likely to find these short period planets just because they're easy to find quickly, right? Kepler's lifetime was about 4 years, so it was just on the border of finding Earth-like planets. We found multi-planet systems where there are many planets in front of a star. The jewel of this kind of thing is Kepler 11. This is an artist's conception of what Kepler 11 might look like. This is an artist's impression. This is not what it does look like, but here's a planet and it has a whole bunch of planets. Here's a star and it has a whole bunch of planets around it. The Kepler 11 system would fit entirely within the orbit of Mercury and Venus. Again, because those are the kinds of systems that are easy to detect. These planets are going around quickly, so we can do the astronomy, we can publish that paper quickly. It takes patience to find the further away planets.
So when you say that that's what we know now, that everything fits in there.
Yes.
And does that take longer to go around?
Yes, there could very well be planets that take 5 years to go around. We would not have seen them yet.
Okay.
Yeah. We've even found, yeah.
If the star is a variable star,
Yes.
is that going to cause confusion?
It does, and we know how to work around it.
Okay.
It does cause confusion. The light curve goes up and down, but the dips of the planets are very distinct from the planet, from the star. And so here is something straight out of science fiction. We found planets now around binary stars. So it turns out binaries are not a problem. We can have planets around binary stars. And this should remind you of Tatooine, famously from Star Wars. There's a planet around 2 stars, which actually kind of sort of look maybe like Tatooine itself. So, there was a to-do about this one. So where do we stand? We've found over 200 planets similar in size to the Earth. We found more than 50 planets now in the habitable zones of stars, planets where there could be liquid water. We found multiple planets around a sun-like star, Kepler 20. These are what the planets might look like. Again, artist's impressions. We can't make pictures of planets yet. But this is Venus, this is Earth, Kepler 20e and 20f, bracket them in size. Right? And unfortunately, Kepler 20, the planets are all much closer than Mercury's orbit. So far we haven't yet found a place just like home. We found planets that are near Earth size around a sun-like star, not in the habitable zone, too hot. We found planets which are near Earth size, we found planets which are around a sun-like star in the habitable zone, not quite like Earth. We found planets which are near Earth size in the habitable zone, but not around a sun-like star. right? Almost there, almost there. And in fact, we came very, very close. This January, last week actually, there was a press release at the meeting of the American Astronomical Society announcing new planets that Kepler has found. As of January 2015, we now have this whole menagerie of small planets in the habitable zones of other stars, just like Earth. If you take nothing else away from the talk, just remember this. We now have Earth-like planets around Sun-like stars and planets in habitable zones of other stars. We have made a great deal of progress in places just like Earth, right? So what happens next to wind up? We're finding exoplanets at an accelerating rate. Soon we will have twins of the Earth, and then we'll have immense pressure to say, let's take spectra of those planets. To take spectra of those planets, we need big new telescopes like the James Webb Telescope. And once we find twins of the Earth, there'll be immense pressure to build telescopes like that. At radio wavelengths, you could go out and take part in the SETI search. As I said, it's all done with private enterprise now. There's no government funding for SETI. But you can get screensavers that run on your computer and do SETI at home. There's a program called SETI at home, and you can get a screensaver, and it takes data from the Arecibo radio telescope and looks through it for signals of interest. Yeah. And then there are new telescopes coming, like the LSST and the Square Kilometer Array. And eventually, we will have large new telescopes like this, but that's a long way away. So what do I want to leave you with? The one thing that that worries us, is that it might turn out that things like E. coli are common. Life may be common. It may be common as a consequence of chemistry. If you have chemistry, you have life. It could be that E. coli is common, but Einstein, Edison, and Emily Dickinson, they are rare. And if so, right now, here's a picture of the Earth taken by one of our robots. It's a sunset on Mars. So this is the surface of Mars, this is the sunset, and that little speck there, that little speck, you are here, and this is everything right now that we know of. Wow. So thank you very much for your attention.
Very much. I was texting my wife and says, "This speaker is great." We're really very, very happy that you could come down and talk about some of the work that you do and engage you all that have come here today. I guess if you have a few minutes, you know,
I'll be happy to take questions. I'm always happy.
And also, I would be remiss if I didn't mention to you that. Again, part of our fundraising that we do here is we actually have a $5,000